200,000 tons of steel, the size of a small city, and it floats. A single iron nail sinks to the bottom, but the world's largest supertankers cross the Pacific fully loaded, at full speed. This is not magic. This is the triumph of 5,000 years of engineering. A journey that began with a hollowed log, ended with steel giants that conquered the oceans. And at every step of that journey, one single law of physics held constant: water carries exactly as much weight as the volume you displace into it. How humanity discovered that law, mastered it, and pushed it to its absolute limits. That is what you are about to see. How does 200,000 tons of steel float? A single iron nail sinks the moment it touches water. A handful of metal drops straight to the bottom. Yet humanity learned to use that same physics to build ocean-crossing giants from the very same material. The answer is not in the material. It is in the geometry, not in density and volume. And finding that answer took 5,000 years. The first shipbuilders did it by instinct, observing that hollowed logs did not sink, experimenting with wider hulls that carried heavier loads, learning a little more of the physics of water with every failure. When Archimedes formulated that physics in a bathtub in Syracuse, he was seeing for the first time the mathematical truth behind centuries of trial and error. And that formula, a floating object receives a buoyant force equal to the weight of the water it displaces, is still used, without modification, in the design of 400-meter supertankers today. In this documentary, we trace 5,000 years of buoyancy engineering. From the intuitive engineering of the dugout canoe to the mathematics of Archimedes, from the structural limits of wooden hulls to the moment steel made the impossible achievable, and through to the digital twin simulations of 2026, we reveal how humanity used the physics of water to conquer the ocean. 5,000 years ago, a human being climbed onto a floating log at the edge of a river. The log did not sink. That single observation: wood does not go under, launched the longest engineering journey in human history. The Egyptians widened and deepened that log, lashing it with papyrus rope to carry heavy granite blocks across the Nile. The Phoenicians sharpened the hull and added a keel, opening the Mediterranean to trade. The Chinese invented watertight bulkheads so that a single breach in one section of a hull would not sink the entire vessel. British engineers laid iron plates across a wooden frame and demolished the belief that metal could never float. And today, the supertankers of 2026 carry 80% of global trade in steel hulls, weighing 200,000 tons. All of them built on one single principle. The buoyant force equals the weight of the water displaced. In this documentary, we examine the structural leap from wooden hulls to steel giants. From the first principles of Archimedes to the digital twin simulations of 2026, we show how fluid mechanics transformed massive steel weight into a global fleet that crosses every ocean on Earth without effort. For most of human history, the ocean was not a highway. It was a filter, a barrier, that drowned everyone who could not understand the physics of water. The civilizations that mastered buoyancy expanded. The ones that did not stayed on shore. Every advance in hull design, every structural innovation, every new material introduced into shipbuilding was paid for by the vessels that failed first, by the ships that split along their keels in heavy seas, by the hulls that took on water and sank with their crews and cargoes. The physics of displacement is simple. The engineering required to exploit it at the scale of a modern supertanker is among the most demanding ever undertaken. Today, we load 200,000 tons of crude oil into a steel hull and send it across the Pacific in weather that would have destroyed every ship ever built before the 20th century, guided by digital systems, stabilized by active ballast management, and monitored by structural sensors that report the stress state of every major hull section in real time. In this documentary, we trace 5,000 years of that engineering journey, from primitive logs to precision steel, from intuition to Archimedes to computational fluid dynamics, from a river crossing to a global ocean fleet that moves without stopping, in every weather, on every ocean, every day of the year. The first boats were not built, they were found. A floating log, a bundle of reeds, a mat of papyrus. The earliest watercraft were natural objects that humans learned to ride before they learned to shape. The cognitive leap from riding a floating object to deliberately constructing one was the first engineering insight in the history of naval architecture, and it happened independently on every inhabited continent. In Mesopotamia, round reed coracles sealed with bitumen were navigating the rivers of the Tigris-Euphrates Valley by 4000 BC. In Egypt, papyrus reed boats were crossing the Nile by the same period. later evolving into the plank-built wooden vessels that carried granite obelisks from the quarries of Aswan to the construction sites of the great temples, downstream. In the Pacific, the builders of the first outrigger canoes were solving the stability problem. A narrow hull is fast but unstable, and the outrigger float provides the restoring force that prevents capsize using empirical intuition that anticipated the formal stability analysis of modern naval architecture by 3,000 years. What all of these builders shared was a working understanding of displacement without the mathematics to describe it. They knew that a wider hull carried more weight. They knew that a deeper hull could carry heavier cargo. They knew that a hull that took on water sank, and that a hull that stayed sealed floated regardless of what it was made of, regardless of how heavy it was, as long as the enclosed volume of air was sufficient to displace water equal to the total weight. Archimedes of Syracuse formalized this understanding in the 3rd century BC, reportedly in a bathtub, observing that his body displaced a volume of water exactly proportional to its submerged volume. His principle, a floating body displaces water equal in weight to its own total weight, was not a new observation. It was the mathematical encoding of what every shipwright on Earth had known empirically for thousands of years. But the encoding mattered. Mathematics could be transmitted, scaled, and applied to problems the original observers had never imagined. Wood is simultaneously the ideal and the limiting material for shipbuilding. It is naturally buoyant, its cellular structure traps air, giving it a density lower than water even when solid. It is workable with simple tools. It is available in large structural sections from mature trees, and it has a tensile strength-to-weight ratio that was not surpassed by manufactured materials until the age of steel. But wood has absolute structural limits that no amount of craftsmanship can overcome. A wooden hull flexes under wave, loading the bow and stern rise and fall on successive wave crests, bending the entire hull longitudinally in a cycle called hogging and sagging. Accumulate enough of these cycles, and the structural fibers of the wood fatigue and the hull begins to work the joints open, caulking fails, and the hull leaks. Every generation of wooden shipbuilders was engaged in a continuous struggle against this structural limit. The Romans solved it partially, with heavy internal framing, closely spaced transverse ribs of oak, giving the hull lateral stiffness. The Vikings solved it differently, with a flexible, clinker-built shell of overlapping planks that could flex with wave motion rather than resisting it, distributing loads across the entire hull surface rather than concentrating them at structural frames. The most spectacular wooden ships ever built were not European at all. The treasure ships of the Ming Dynasty, the great vessels of Zheng He's early 15th century ocean expeditions, were reportedly 3 times the length of the largest contemporary European ships. Their multi-masted rigs, watertight bulkhead compartmentalization, and sophisticated hull forms represented a level of naval engineering that Europe would not match for another century. The Chinese invention of the watertight bulkhead was particularly significant, dividing the hull interior into sealed compartments so that a breach in one section did not flood the entire vessel. The same principle is the basis of modern ship subdivision requirements. By 1800, the wooden warship had been optimized to near the absolute limits of the material. First-rate ships of the line carried over 100 guns on 3 decks, displaced over 3,000 tons, and required the timber of several thousand mature oak trees to build. The structural engineering was extraordinary, and it was at its limit. The next advance in displacement engineering would require an entirely different material. In 1787, a small iron boat was launched on the River Severn in England. It did not sink. This was, to many observers, deeply counterintuitive. Iron is nearly 8 times denser than water, and the assumption that metal objects sink was so thoroughly embedded in common understanding that the launch of a floating iron hull was treated as a curiosity rather than the engineering revolution it actually represented. The physics, of course, had not changed. An iron hull floats for exactly the same reason a wooden hull floats, because the enclosed volume of air within the hull displaces water whose weight exceeds the total weight of the hull structure. The iron hull is heavier per unit of surface area than a wooden hull, but it can also be made thinner, which means the ratio of enclosed volume to hull weight can be made more favorable than wood allows. The structural advantages of iron over wood were decisive. Iron does not rot. Iron does not work. The riveted iron plates of a ship's hull do not flex and open at the joints under wave loading the way wooden planks do. Iron can be produced in industrial quantities to precise specifications, allowing hull forms of a complexity and hydrodynamic refinement impossible to achieve in timber. And iron can be formed into structural sections, frames, beams, deck plates that give a hull longitudinal stiffness far beyond anything achievable in wood. The transition from wood to iron was accelerated by steam propulsion, which required not just a different hull material, but a different hull form. A steam-powered vessel does not need to be shaped to maximize sail-driven hull speed. It can carry its own power source, operate in any wind condition, and be optimized for cargo capacity, rather than sailing performance. The iron steamship could be made wider, deeper, and blunter than any sailing vessel, and the resulting displacement volumes allowed cargo capacities that transformed global trade. HMS Warrior, launched in 1860 as the world's first iron-hulled armored warship, was the definitive demonstration of what iron displacement engineering could achieve: a vessel so structurally superior to any wooden contemporary that it rendered the entire existing battle fleet obsolete at a stroke. The largest ships ever built are the ultra-large crude carriers of the late 20th and early 21st centuries, vessels over 400 meters in length, over 60 meters in beam, displacing over 500,000 tons when fully loaded. At this scale, the engineering of displacement is no longer intuitive. The hydrostatic forces acting on a hull of this size in heavy seas are measured in millions of tons. The longitudinal bending moment, the hogging and sagging force that failed the joints of wooden ships, reaches values that would tear a conventional steel structure apart. The structural response is a hull girder of extraordinary complexity, deep longitudinal girders running the full length of the vessel, transverse frames at close spacing, deck plating and tank top plating working as part of an integrated structural system that distributes loads across the entire hull volume simultaneously. The stability analysis of a modern supertanker is a computational problem of comparable complexity to the structural analysis. A vessel carrying 200,000 tons of liquid cargo must maintain positive metacentric height, the condition that guarantees a righting moment. When the vessel is heeled by wave action across the entire range of loading conditions it will experience during a voyage, ballast water systems, carefully managed cargo distribution, and active monitoring of the vessel's trim and stability state are all required to keep a vessel of this size upright in the North Atlantic in winter. Digital twin technology, now standard in the design and operation of the largest vessels, as of 2026, allows engineers to simulate the behavior of a complete hull under any combination of sea state, loading condition, and structural degradation before a single plate is cut. A digital model updated in real time from hull stress sensors, motion reference units, and loading computers gives the ship's officers a continuous picture of the structural state of their vessel, identifying fatigue hotspots, flagging dangerous loading conditions, and predicting remaining structural life with a precision that was impossible even 20 years ago. The displacement hull, a vessel that floats by pushing water aside, has been the dominant form of maritime transport for 5,000 years. In 2026, it still is. But the engineering frontier is now focused not on whether a hull floats, but on how efficiently it moves through the water it displaces. The dominant source of energy loss in a large displacement vessel is not structural, it is frictional. Water clinging to the hull surface creates a viscous drag that accounts for a significant fraction of total propulsion energy. At the scale of a supertanker, reducing hull friction by even a few percent represents millions of dollars in annual fuel savings and a proportional reduction in emissions. Air lubrication systems, which pump a continuous layer of air bubbles across the underwater hull surface, replacing water on steel friction with air on steel friction, are now installed on a growing fleet of commercial vessels, reducing frictional resistance by up to 10%. Hull surface coatings inspired by the skin of fast-swimming marine animals reduce turbulent boundary layer formation. Optimized bow forms, computed by computational fluid dynamics, minimize wave-making resistance at design speed. Autonomous ship systems, vessels with no crew, guided entirely by sensor networks and AI navigation, are being tested in commercial service as of 2026. The displacement calculation for an autonomous vessel is managed continuously by onboard systems that monitor cargo weight, fuel consumption, ballast water distribution, and sea state simultaneously, maintaining optimal trim and stability without human intervention. And at the furthest frontier of displacement engineering, the concept of permanent floating habitation. Modular floating city platforms, applying the same buoyancy principles that kept the first reed boats on the surface of the Nile, are being designed to house permanent communities on the open ocean. 5,000 years ago, the first engineer who hollowed a log and climbed into it was solving the same problem that the designers of a floating city must solve today: displace enough water to carry the weight, keep the hull sealed, and stay on the surface. The physics has not changed. Only the scale of human ambition has.